Hi, today we're going to start a 2-day lesson on visualizing distributions. And as we said previously, a distribution is just a listing or a picture of all the possible values that a variable could take on and the number of times that those things occur. You'll remember that we used dot plots to show distributions. Today we want to talk about specifically two styles or shapes for those distributions to take on. The first is the uniform distribution. And ladies and gentlemen, I want to give you an example of this before we actually start writing anything down. My awesome dice rolling program is set up to use random numbers to simulate rolling a regular six-sided die. So what this program will do is allow you to enter a number of times that you want to roll and show you the number of each outcome that you get. You know from your previous studies of probability that all the numbers on a dice are equally likely to come up unless you have a loaded dice, and we don't have that here. So each number is equally likely to come up, and that means that, well, let's just see. If we were to roll, say, 6 times, what would you expect to see? Speaking of probabilities, 4 times out of the 6 rolls, what should happen did happen. That is, we got different numbers 4 different times here. One number, 1 repetition, one number, no repetitions. Equally likely to come up, and you can see not only do I show you a count, but here we've got a little graphical display of the number of times each number came up. When you do 6 rolls, it's not that exciting, folks, but let's just kick it up a little bit, and let's double 12 rolls and see what happens there. Oh, all right. Boy, 5s and 6s are kind of being left behind. As you look at the graph of this distribution, again, you can see that we've got a little clump of things going on down here, and it's shorter, of course, down there at 5s and 6s. You really start to see what should happen when you increase the number of rolls. And so I'm going to go to 100 rolls. And let's take a look at that. Well, now the place where we had more has changed. Instead, our 3s are more common, our 4s and 6s less common. But you can see that it is varied. However, the lowest number of rolls is 11, and that was out of 100, so 10% of the time we got there. If you figure your probabilities right, it should get there about 16% of the time. How many times do we want to roll? Well, let's just go full bore this time and go for the 1,000. Anything more than that, this little program is not going to be able to deal with. But as we get to the 1,000, look what happened here, folks. Things are starting to even out, right? And that's exactly what you would expect to have happen if all these outcomes are equally likely. The graph of this display, you can see that those bars are approximately the same length. It's not exact, but approximately the same length. So there's our uniform distribution. In a uniform distribution, this occurs when each outcome is equally likely. Equally likely is a good probability term. Just means one is not any more likely to come up than another. When each outcome is equally likely, that's when you get the uniform distribution. They are usually or approximately rectangular in shape. And that happens again because probability says they're each as likely to come up as another. So a rectangular shaped graph might look like, and I'm going to draw it straight like it was true theory. If we were doing our dice rolling and we did it many, 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 many times, then these outcomes are what we'd expect, all about occurring about the same number of times, whatever that number happens to be. If we were going to describe a distribution, we normally want to talk about its shape, its center, and its spread. Folks, we've discussed the shape here. So if I were going to write a summary sentence about this, I'd begin by saying it's approximately rectangular, it referring to the distribution, approximately, rectangular. Now we could talk about the center of this distribution, which if you think about it mathematically, 3.5 is the center of that, or the mean of that distribution. However, that doesn't mean as much here. It's not as telling as just saying it's approximately rectangular with about, and then you'll fill in the number, okay, the number of outcomes in each category. For our dice rolling program in each category, for this dice rolling program, folks, when we went 1,000 times, we should have had around 167 in each category. So you describe the shape as rectangular in a uniform distribution. The center is not as important, okay? That's not going to give you a whole lot of information, although you could note it. As far as spread, we're saying our outcomes are spread equally across the categories. Let's take a look at some situations where uniform distributions might come up over the days of the week. Over the days of the week means Monday, Tuesday, Wednesday, Thursday, Friday. In a normal school week, we should have approximately the same number of cars in the parking lot each day. Another situation where you might expect a uniform distribution across the digits 1 through 9. Well, folks, anytime when numbers are selected at random, we know we should get about 10% of our numbers for each of those digits. So maybe you might be thinking about, and our textbook uses this example, the last digit of a phone number. You couldn't say the first digits because they have a meaning, or at least they used to when area codes and exchanges meant a lot. But the last digit in phone numbers, those should be distributed just about equally across all of the digits, 0 through 9. Situations that you would expect to be not uniform, this might be a little bit easier to answer, quite frankly, because this is a little harder to think about. These things we're more used to. Over the months of the year, perhaps high temperatures, which go in a cyclic pattern instead of uniform pattern. High temps over the days of the month. Things that you could think about. Now, this doesn't just mean Monday through Friday, right? This means all the days of the month. So possibly things that are non-uniform there would be the number of cars at Saginaw and Vienna. Right? I'll bet you that's different for different days during the month. Over the digits 1 through 9, where we wouldn't expect uniform things, that would be like the first digit in phone numbers, or at least it used to be that way. Everybody, the first digit in phone numbers. Everybody where I live used to have a 7 as their first digit. Out here, first digits 6, right? At least it used to be. Over the days of the week, now we're talking Monday through Friday, things that you might expect to be non-uniform. I'll tell you one thing. I have noticed the number of students who stay after school is significantly less on Friday than other days. So over the days of the week, the number of students who stay late or who stay after school is not uniform. All right, I hope that gives you a little introduction to the uniform distribution. Some places where you expect it, some places where you wouldn't. We're going to shift gears a little bit now and talk about the normal distribution, which is one of the most important that we will study in statistics. A lot of research has been done about the normal distribution. A normal distribution is shaped somewhat like this, and I'll tell you, I don't ever draw it perfectly, but you've heard of called the bell-shaped curve. That's usually what people call a normal distribution. That's the slang term for it. This is a distribution where most of the values happen right at the center. In fact, the mean, median, and mode will all be approximately the same here. And then things start to taper off as you go from end to end. So if we were going to talk about shape, we'd say bell-shaped curve. Mean, median, and mode all in the same place. The characteristics of this thing then, high point in the center, symmetric on both sides. Symmetric or fairly symmetric, nothing comes out perfect, but symmetric on both sides. When we start studying the normal curve in depth, we will talk about inflection points. That's where the curvature changes. Here we're cupping upwards. See how we could kind of hold water right there? Here the cupping is downward. So an inflection point is when that happens. And in the normal curve, inflection points happen, or the first inflection point happens. One standard deviation from the mean, it's called. This will be a word that you've heard before. A standard deviation is just a chunk of area under a normal curve. And we can talk a little bit, pretty specifically about what happens there. Within that one standard deviation of either side of the mean, about 68% of the values in a normal curve will lie. If you think about things that act this way, okay, symmetric on both sides, high point in the center, oh, what else do we want to say? 2 inflection points. It's not hard to think about things that are like this, where most of the data, or I think most of the people, are around the middle. There are a few at the low end and a few at the high end, but the majority of things right around the middle. Situations that do that, you guys, almost anything that you measure, anything that can be measured just about, you might include there things like height. I'm short, folks. I still am within the middle 68%, but barely, okay? Anything that can be measured, so a height or a weight, or an IQ, right? Or test scores are often normally distributed on good tests anyway. All of those things produce, or tend to produce, lots in the middle, a little on either end. I have a normal distribution that I'd like to show you that I took out of our textbook today. It is showing groups of 5 workers selected at random from Westvaco, from the 10 hourly workers in round 2. These are the ages of 5 selected at a time, and you can see that they did numerous trials, 200 trials of selecting 5 ages at random. It asks us to do this. We got the bell-shaped curve going here. The center measure for a normal curve is generally the mean, and so we're supposed to estimate the mean. The standard deviation is called the spread, or it kind of is a way to describe the spread in a distribution like this. So I'd have you look at this, and even though the dots certainly aren't perfect, you can see that the normal curve somewhat fits pretty well across there. The mean is going to be right about in the middle, and I'm looking at around 47, at least that's my guess. I can give you a bit of technical information about the normal curve. Normally, didn't mean that as a pun, but usually almost the entire data set will be contained within 3 standard deviations on either side of the mean. So if we take the difference between the mean, which I said is 47, I think, and this low point, 35, subtract those two, that's 12. 3 standard deviations ought to fit in here, or it would be something like this, right? So that would be 12 divided by 3, 4. So a standard deviation is about 4 years in this distribution. Again, what we did was we looked at a mean, okay, 47 about. Then we compared that to the low end of the scale, so 47 minus 35. That's 12 years that we want to spread up between 3 standard deviations. We choose 3 because I'm telling you that almost 100% of the data in any normal distribution will be contained within 3 standard deviations either side of the mean. Does that work up here too, you might be asking? We'll try it. Up there it was 60. If we take away the mean, 47, that's also roughly 12, it's 13. So if we divided that by 3, again, we'd end up with about 4 for a standard deviation. So when we're talking about the normal curve, a summary sentence should include the normal shape, the distribution is shaped normally, or is approximately normal. In this case, it's not exact. Centered at, and what we're going to put in there is the mean for a normal curve, okay? Centered at about 47 for this distribution with a standard deviation of about 4. Standard deviation about 4. So when we describe a normal curve, those are the things we want to say. Its shape, its center, its spread, its standard deviation. Good. I hope that you've learned a little something here. I'm going to remind you that you can always rewind, pause, go back, look and listen again. Read your textbook. It's meant to be read. I'll see you in class tomorrow.